This is part 4 of the Git Essentials workshop. Small examples are discussed to show essentials in action. Git opens many ways to go. Please don't make too many demands on the given examples. The hands-on can be replayed with copy and paste. 2 environment variables allow to choose convenient workspace. The used Git version is 1.9. Any complete Git installation contains man pages. The docs are also available as linked web pages local on the disk. To give you a feeling, there are far more than 100 Git commands. It is absolutely mandatory to configure username and email before any work can start with Git. Expect lots of parameters that may be optionally set. Just as an example, you may want to configure your favorite editor and merge tool. Note, you may also edit and review the config file directly. Let's begin with a simple repository to analyze its elements and structure. First, we need some fresh and empty repository. Let's also create an empty first directory. Note, the empty directory is not even mentioned in Git status. It's good practice. We need at least one real file that may be empty. As soon as there is a real file, Git status informs us that the file is still new and unknown to Git. And you get always advice how to proceed. For convenience, the current directory is added to the index. Note, this is just the contents at this moment. Git has no order to catch from now on everything that may be added to or changed in the future. Git has accepted the new one data file. The location of Git objects is known and find shows them all. There is now just one Git object with its hash. Note, there is a new blob object in the repository without any commit. Even if you unstage the uncommitted file, that thereafter is never needed anywhere, it still stays in the repository and becomes a dangling object for future garbage collection. The focus of Git is files, and Git ls files lists full file paths, not directory paths. Finally, Git ls files reports the contents of the index. It gives you all tracked files of the current branch, starting with the current directory. And therefore, after a commit, the list of reported files with Git ls files is unchanged. The git status command now reports a clean working directory. Let's analyze the results. There are a couple of methods to look around. We can browse all object files. We can give a listing, a short listing. We can list all files in the current branch. And note, there still is only one file in the index. There is only one file, data git ignore, but there are 4 git objects. Let's have a look. Where does the current head point to? To ref's head's master. What is the commit object of the tip of the current branch? This is something starting with 5449. We can get this info verbosely with one single command, where the star marks the current branch in a list of multiple branches. Its name is master, and the tip commit hash starts with 5449. There also is the commit message, which has been given with the last commit. Any commit is the start point of a complete full snapshot. Git show gives you the contents of any object. There is the commit hash, the hash of the root tree, and other infos. Let's have a look at the root tree object. There's only one entry for the subdirectory name data. And we are explicitly told that data is a tree object. What exactly does this tree contain? This tree contains just a single blob entry. And it is a data object whose name is .gitignore. Let's put everything into an overview diagram. The top level commit points to the one single root tree object. The root tree refers to another tree named data. That tree finally lists a blob with the name .ignore. Hold on, the size of the blob is 0. It's an empty file. Worldwide, this file has the unique constant hash starting with E69D. That much for one empty file. Within the just analyzed one file repository, some new data is created and committed. Shown is the output of the command git ls files and tree. Tree is a well-known Unix command. Files with the same contents have the same color and the same hash, of course. The analysis of the result is done the same way as before. We get all objects with this repository with the find command. We shorten the output and we get the SHA1 of the head in the current branch. Then we get a commit object with the details and come to the root tree object to be the start point of our analysis. Now we should skip the gory details this time and fast forward to the graphical overview. We identify the 4 first Git objects we had the first time here. We also can recognize the parent-child relation between the 2 commits. Blobs are shown here on the right side, and we can see how different objects are reused wherever possible if they are the same. There is only one hash for anywhere given content. Until now, there are only shared blob objects. If we purposely change specific data, we can also get shared tree objects. With this in mind, let's add something to the file base1.txt, which in some trees is not contained, and see what happens. Let's skip the details again and straightforward go down to the graphic overview. The third commit describes the changes which have been done on the file base1.txt, and we see this is a new blob object. But we see also we now have here a shared tree object, and here also. Good. Let's create a branch and see what has changed. The hash of the last commit is starting with 5e51ec. The command touch this timestamp is a Unix command. It is just to memorize the timestamp of now. The command git branch b.1 creates a new branch. Then the command find dash newer this timestamp is again a Unix command that lists everything that is newer than this timestamp. And that is everything since creating the new branch. We now have 2 branches, master and b.1, and we see from the hashes that these branches are the same. The hashes have been listed with the cat command. So head points to master, master and b.1 point both to the common commit. Note that adding a branch is just adding a reference. And also true is any commit object may be the target of a branch reference. The head of any branch is the reference that points to the last commit object, and it is stored under refs, heads and the branch name. There is one single symbolic reference, the git head, which points to the current checked out branch, and this is in our case master. We are still on master. b.1 is not checked out. To prove the last statements, let's verify we still are on master. Check out branch b.1 and verify again, we are now on b.1. Head points to b.1. After a commit of new data, the current branch has moved. Git log is a common command to query the history. We already know how to list the contents of a commit. And there are several ways to name the needed references. So this is just an example for the mentioned feature. The analysis of the root tree object now yields that master and b.1 trees now have diverged. Nothing special, just branches are references, are pointers to commits, and those pointers often change their values. There are commands to create lightweight tags and to create annotated tags. Tags may be listed and tags may also be deleted. That's it for now. About merging files, take as given some prepared scenario. There may be a branch master with the files f1 till f4. A branch A has files f3 and f4 which are identical to those in branch A master. Branch B has all of those plus f5, 6 and 7. And we analyze merging A into B and vice versa, B into A. The commands for creating these branches are separated. Branch master is created with these commands. Branch A1 is created with these commands. A2 is the same as A1. We need two merging operations, so we build two identical branches, A1 and A2, and the same for B. These commands and these commands. B has all files F1 to F7. The first merge will bring the changes made in branch A1 since the common ancestors into branch B1. The timeline in the history goes from bottom up. In branch A1, the files F1 and F2 have been deleted, since after the common ancestor branch master. Therefore, with this merge operation, the files F1 and F2 are removed from branch B1, and the result is F3 till F7. In the other case, the merge B2 to A2, the files F5, 6 and 7 have been added after the common ancestors. Therefore, with the merge operation B2 into A2, they are also added to A2. Note, within this merge, the files F1 to F4 are not covered at all because they were not involved in the relevant changes after the common ancestors. Note also that the final result is the same in both cases, the files f3 till f7. As a summary, it can be said that the merge result always is stored at the currently checked out branch. Merging is about the take-in of commits that describe discrete changes. The results therefore are: we get all of A plus files added to B after the common ancestors commit minus files deleted from B after the common ancestors commit. It is possible to merge multiple branches, but a merge downstream before the ancestors commit is not possible. Whatever that means, anyway. This merge scenario is about a file easy.txt, where changes within a file may automatically merged, and conflict.txt, where manual processing of a conflict is required. The history of the operations are anticipated in the given diagram. The commands for generating the paired equal A's and B's are again separately listed to ease reproducible results with copy and paste. So first we generate the branch master, thereafter the branches A1 and A2, they are the same, and third the branches B1 and B2, again they are the same. The merge of A1 to B1 gives success for easy.txt, but fails due to incompatible changes for conflict.txt. The contents in the boxes for the file easy.txt for master A1 and B1 before the merge are listed here with these commands. Easy.txt has changed only in the branch A1. Easy.txt is the same in master and B1 branches. Therefore, the added lines from branch A1 may automatically be incorporated by the merge command. Now to the conflict. The contents in these boxes are generated with these given commands. Incompatible changes have been intentionally added, and the merge generates an unresolved draft version in the working directory, where the file has to be manually processed. After the conflict has been resolved, the file is added to the index and the merge may be committed. In the other case of merging B to A, the file easy.txt already has all the lines 1 to 5, whereas here is no change between the master version and the B2 version. Merging in a missing change is a no operation, say it has no effect. The handling of conflict.txt is the same as in the previous case. For fetch, I just want to show how to fetch some branch from the remote repository into a local branch with a different name. With this command type, fetch needs a repository, the remote branch name, that is to be fetched, and the local branch name. We intentionally want to be different. The dry run option just simulates the operation without effect. When working with multiple remotes, there occasionally may be the need to push branches with different names on the local and remote repository. The scenario shown in this diagram serves as a general example. The local branch study and study 1 will be pushed to some remote repository branch with a totally different name, study 6, ABC study 6. And study 2 is pushed to different pairs with different names, study 7 and master. The repository preparations are done on an own page. First, the 3 repositories have to be initialized, bear 1, bear 2 and user 1. Then on user 1 we create the dummy master, we create study 1 and we create study 2, that's another branch. The push commands are check out the master and then the 3 push operations to bear 1 and to bear 2. The general syntax is git push remote repository, the name of the local branch, colon, and the name of the remote branch. So these 3 lines do the total job. A good command to check the results is ls remote. It lists branches and tags available in remote or in local repository. It works everywhere. The result of the above push scenario may be verified with the commands given here. It's worth to mention again that git ls remote works locally also. You may want to verify your own studies on local repositories also with this method. Some final notes. If some existing remote branch is updated, there must be a shared history between local and remote branch. This may fail. If some new branch is pushed which does not exist on the remote, it will be created. This never fails. For testing different syntax variants, you may push many new branches to the remote, and you always can delete remote branches when you are done. We have reached the end now, and what's left to say is thanks for watching and have fun and success with Git.